a Saturn-sized gas giant lurking in the habitable zone of Alpha Centauri A, our nearest sun-like neighbour, just 4 light-years away. The James Webb Space Telescope just captured something that astronomers have been hunting for decades: direct evidence of a planet orbiting the star next door. But here's what makes this discovery absolutely mind-blowing. This world shouldn't exist. The violent gravitational chaos of a triple star system should have torn it apart billions of years ago. Yet there it is, hiding in plain sight in our cosmic backyard. And if this planet is real, everything we thought we knew about how solar systems form might be completely wrong. In August 2024, a team of astronomers pointed the James Webb Space Telescope's most powerful infrared instrument at Alpha Centauri A, implementing a custom observing sequence that had never been attempted before. What they found sent shockwaves through the scientific community. Using Webb's mid-infrared instrument, known as MIRI, equipped with a specialized coronagraphic mask to block out the overwhelming glare from one of the brightest stars in our night sky, the team detected a faint point of light. This wasn't just any astronomical object. It was over 10,000 times fainter than Alpha Centauri A itself, positioned roughly twice the distance between Earth and the Sun from its host star. The discovery was published in 2 papers, accepted by the astrophysical journal Letters in August 2025. And it represents potentially the most significant exoplanet detection of the decade. Dr. Charles Beischmann from NASA's Jet Propulsion Laboratory, who co-led the research, called these incredibly challenging observations to make, even with the world's most powerful space telescope. But before we dive into what makes this discovery so revolutionary, we need to understand exactly where we found this planet and why Alpha Centauri has obsessed astronomers for generations. Alpha Centauri isn't just any star system. It's our closest stellar neighbour, sitting a mere 4.37 light-years from Earth. To put that in perspective, if you could travel at the speed of light, it would take you just over 4 years to reach it. The nearest star after Alpha Centauri? That's Barnard's star, sitting at 6 light-years away. Alpha Centauri is literally in our cosmic backyard. But here's where it gets interesting. Alpha Centauri isn't 1 star, it's 3. The system consists of Alpha Centauri A and Alpha Centauri B, 2 sun-like stars locked in a tight binary orbit, circling each other every 80 years, at an average distance of about 23 astronomical units, roughly the distance between our Sun and Uranus. Then there's Proxima Centauri, a small red dwarf star that orbits this binary pair at a much greater distance, about 15,000 astronomical units away. Alpha Centauri A, the star where Webb detected the planet candidate, is almost identical to our Sunday. It's about 10% more massive, slightly hotter, and approximately the same age, around 4.85 billion years old. When you look up at the southern sky and see Alpha Centauri shining as the 3rd brightest star in the night sky, you're looking at a stellar twin of our own Sun, just hanging out 4 light-years away. This proximity has made Alpha Centauri a prime target for planet hunters for decades. Think about it. If we're going to find habitable worlds, if we're going to discover Earth-like planets where life might exist, shouldn't we start by looking at the Sun-like star next door? But there's been a problem. A massive, frustrating problem that has plagued astronomers for years. The binary nature of Alpha Centauri, A and B, creates an almost impossible observational challenge. These 2 stars are so close together and so bright that their combined glare makes spotting planets around either of them extraordinarily difficult. It's like trying to spot a firefly next to a blazing searchlight from miles away, except the searchlight is actually two searchlights spinning around each other. Previous attempts to find planets around Alpha Centauri A and B had failed despite years of observations. Radial velocity measurements, which detect the tiny wobbles a planet's gravity causes in its host star, were sensitive enough to rule out massive planets, but not smaller worlds. The glare from both stars overwhelmed direct imaging attempts, making it impossible to see anything in their vicinity. In fact, a controversial detection in 2012 claimed to have found an Earth-sized planet around Alpha Centauri B, but that discovery was later retracted after further analysis showed it was likely an artifact in the data. The disappointment in the astronomical community was palpable. Meanwhile, Proxima Centauri, the red dwarf component of the system, had been more forthcoming. Astronomers discovered Proxima Centauri B in 2016, an Earth-sized world orbiting in the star's habitable zone. 2 additional planets were later confirmed around Proxima D, a sub-Earth planet very close to the star, and the disputed Proxima C, a potential super-Earth or mini-Neptune. But Proxima Centauri is a red dwarf, a small, cool star that's notoriously violent. It unleashes powerful stellar flares that could strip away planetary atmospheres, bombarding any worlds with deadly radiation. Even though Proxima B sits in the habitable zone, most scientists doubt it could actually harbour life. Alpha Centauri A and B, on the other hand, are different. They're sun-like stars, stable, well-behaved, and potentially capable of hosting truly habitable worlds. But finding planets around them seemed impossible, until James Webb changed everything. The breakthrough came down to a combination of cutting-edge technology and meticulous planning. The James Webb Space Telescope, launched in December 2021 and beginning science operations in 2022, represents the most powerful space telescope ever built. Its 6.5-meter gold-plated mirror collects infrared light with unprecedented sensitivity, allowing it to see objects that were completely invisible to previous telescopes. But even Webb's incredible capabilities weren't enough on their own. The team needed to develop a completely custom observing strategy, specifically designed for Alpha Centauri A. Here's how they did it. Webb's mid-infrared instrument has a coronagraph, essentially an artificial eclipse, that blocks out the light from a star, allowing astronomers to see much fainter objects nearby. Think of it like using your hand to block the sun so you can see something next to it. In August 2024, the team placed this coronagraphic mask directly over Alpha Centauri A, blocking its overwhelming glare. But there was a complication. Alpha Centauri B, the binary companion, was still flooding the field of view with light. Even with Alpha Centauri A, blocked the light from Alpha Centauri B scattered around the coronagraph's edges, creating complex diffraction patterns and residual starlight that contaminated the image. So the researchers did something brilliant. They created a sophisticated computer model that predicted exactly how light from both stars would scatter through Webb's optics. They then digitally subtracted this contaminating light from their observations, performing what's essentially a high-tech cleanup of the image. After processing over 100 hours of cumulative observations and analyzing only the highest quality images from the dataset, they revealed what had been hidden beneath the glare. A faint point source, designated S1, sitting approximately 2 astronomical units from Alpha Centauri A. But finding a dot of light isn't enough to declare a planetary discovery. The team needed to prove this wasn't just an artifact, a background galaxy, a passing asteroid, or some kind of instrumental glitch. They needed to confirm this was actually a planet. The evidence is compelling, though not yet conclusive. First, The object's brightness in the mid-infrared perfectly matches what we'd expect from a warm gas giant, something roughly the mass of Saturn. Its temperature suggests it's not a background galaxy, which would appear much cooler, and it's far too bright to be reflected light from a distant star. Second, and this is where things get really interesting, this detection isn't completely new. Back in 2019, a team led by Kevin Wagner from the University of Arizona spotted a potential planet candidate around Alpha Centauri A, using the European Southern Observatory's Very Large Telescope in Chile. That observation was part of a project called Near-Near-Earths in the Alpha Centauri region, which used thermal imaging to search for planets. The 2019 detection was tentative. The signal was there, but it wasn't strong enough to confirm. Scientists labelled it a candidate and moved on, hoping future observations might provide clarity. Now, Webb's 2024 observations have detected an object in almost exactly the same location. The odds of two completely independent instruments using different technologies on opposite sides of space, detecting the same false signal, astronomically low. But then came a curveball. The team conducted 2 additional observations with Webb in February and April 2025, and the planet disappeared. It was simply gone from both images. For most discoveries, this would be the end of the story. No detection equals no planet. But the researchers didn't give up. Instead, they did something remarkably clever. They used computer simulations to model millions of possible orbits. Here's what they discovered. If this planet exists, it's not on a nice circular orbit like Earth. It's on a highly elliptical orbit, meaning it swings in very close to Alpha Centauri A and then loops back out to greater distances, like a cosmic pendulum. The team calculated that the planet has an orbital period somewhere between 1.5 to 2.5 Earth years, with an orbital eccentricity of about 0.4, moderately elongated. In roughly half of the simulated orbits, the planet would have been too close to Alpha Centauri A during the February and April 2025 observations for Webb to detect it. The star's overwhelming brightness would have completely drowned out the planet's faint signal, rendering it invisible. This actually makes the case stronger, not weaker. If the planet follows an elliptical orbit, as the simulations suggest, then the non-detections perfectly align with predictions. The planet was visible in August 2024 and in 2019 when it was farther from the star, but invisible in early 2025 when it had swung back in close. The team also had to account for gravitational stability. In a binary star system, planets can't just orbit anywhere. The gravitational influence of the companion star puts severe constraints on where stable orbits can exist. The researchers ran simulations that factored in Alpha Centauri B's presence, ensuring that any proposed orbit wouldn't result in the planet being flung out of the system. Their conclusion? A Saturn-mass gas giant with a radius of about 1 to 1 times Jupiter's radius, and a mass between 90 and 150 times Earth's mass, orbiting Alpha Centauri A in an elliptical path that varies between 1 and 2 astronomical units from the star. If confirmed, this would be absolutely unprecedented. Let me break down exactly why this discovery is so revolutionary. First, the proximity. This would be the closest directly imaged exoplanet to its host star ever detected. Most directly imaged planets orbit at enormous distances from their stars, 10, 20, even 50 astronomical units or more. That's because the farther a planet is from its star, the easier it is to separate the planet's light from the star's glare. But this planet candidate sits just 1 to 2 astronomical units from Alpha Centauri, are closer to its star than Mars is to our Sunday. Successfully imaging a planet this close to such a bright star is a technical achievement that was thought to be nearly impossible. Second, the habitable zone. The habitable zone around Alpha Centauri A extends from roughly 1.2 to 2.1 astronomical units, the range of distances where liquid water could exist on a planet's surface. This gas giant orbits right in the middle of that zone. Now, a gas giant itself isn't habitable. It's a ball of hydrogen and helium with no solid surface where life as we know it could exist. But here's the tantalizing possibility. Gas giants often have moons, lots of them. In our solar system, Jupiter has 95 known moons, and Saturn has 146. Some of these moons, like Europa and Enceladus, are believed to harbour subsurface oceans that could potentially support life. If this gas giant around Alpha Centauri A has similar moons, and if those moons are located in the habitable zone, they could have liquid water on their surfaces. Imagine a rocky moon, roughly Earth-sized, orbiting a gas giant that itself orbits in the habitable zone of a Sun-like star, just 4 light-years from Earth. The potential for life on such a world is genuinely exciting. Third, the age and temperature. This planet candidate, if confirmed, would be the most similar to the giant planets in our own solar system in terms of temperature and age. It orbits a star almost identical to our Sun in an environment remarkably similar to what we have here. This makes it an incredible comparison object. For the first time, we could directly study a gas giant around a Sun-like star and compare its composition, atmosphere, and properties to Jupiter and Saturn. This could provide crucial insights into how our own solar system formed and evolved. Fourth, and perhaps most mind-blowing, the fact that this planet exists at all challenges everything we thought we knew about planetary formation in binary star systems. Binary stars are complicated. When 2 stars orbit each other, their combined gravitational fields create a chaotic environment for planet formation. The gravitational perturbations can disrupt protoplanetary disks, the swirling clouds of gas and dust where planets form, making it incredibly difficult for planets to coalesce. Most theoretical models suggest that planets in binary systems should either orbit very close to one star or very far from both, in stable regions where the gravitational chaos is minimized. A planet orbiting at 1 to 2 astronomical units from Alpha Centauri A is right in the middle of the danger zone where Alpha Centauri B's gravitational influence should have prevented it from forming or ejected it from the system long ago. Yet if this planet is real, it somehow survived. It managed to form a void being flung into space and maintain a stable orbit for billions of years in one of the most gravitationally challenging environments imaginable. Dr. Aniket Sanghi from Caltech, the study's co-author, put it perfectly. Its very existence in a system of 2 closely separated stars would challenge our understanding of how planets form, survive, and evolve in chaotic environments. So, how did it survive? There are a few theories. One possibility is that Alpha Centauri A and B weren't always as close together as they are now. Some simulations suggest that binary stars can form with wider separations and then migrate closer over time, especially if they formed in a dense stellar cluster, where gravitational interactions with other stars could have altered their orbits. If Alpha Centauri A and B started out farther apart, The protoplanetary disk around Alpha Centauri A would have been more stable, allowing planets to form in what we now consider the danger zone. Then, as the binary stars moved closer, the planet was already fully formed and massive enough to resist being ejected. Another theory involves planetary migration. Perhaps this gas giant originally formed much farther out from Alpha Centauri A, in a region where the gravitational influence of Alpha Centauri B was weaker. Over millions of years, interactions with the protoplanetary disk, or other planets, could have caused it to migrate inward to its current location. There's also the possibility that the planet's highly elliptical orbit is actually a clue. Elliptical orbits often result from gravitational interactions, either a close encounter with another planet or ongoing perturbations from Alpha Centauri B. The planet might have originally been on a more circular orbit, before something kicked it into its current elliptical trajectory. What makes this even more fascinating is that the very challenges that make this planet's existence unlikely also make it incredibly valuable for science. If we can figure out how this planet formed and survived in such a chaotic environment, we'll learn fundamental things about planetary formation that we can't learn from studying our own solar system. But, as exciting as this discovery is, we need to be clear, it's not confirmed yet. The planet is still a candidate, and there's a non-zero chance that further observations might reveal it to be something else entirely, though that's looking increasingly unlikely. The next round of observations is scheduled for fall 2026, and the timing couldn't be better. Based on the orbital simulations, the planet should be near the optimal position in its orbit for detection, far enough from the star that Webb can separate its light from the stellar glare. If the planet shows up in those observations, we'll have 3 independent detections spanning 7 years, which would be virtually impossible to explain as anything other than a real planet. At that point, we could upgrade it from candidate to confirmed, and the real science begins. But Webb isn't the only telescope that will be looking. NASA's Nancy Grace Roman Space Telescope, set to launch by May 2027, will also observe Alpha Centauri. Roman's visible light observations will complement Webb's infrared data, allowing scientists to measure the planet's size, reflectivity, and potentially even detect features in its atmosphere. Together, Webb and Roman could provide an unprecedented level of detail about this planet if it exists. We might be able to determine its exact mass, measure its atmospheric composition, detect weather patterns, and even search for moons. And here's where things get truly exciting. If this planet is confirmed, it becomes the most important exoplanet ever discovered, bar none. Why? Because at just 4 light-years away, it's close enough for future missions to actually visit. Right now, humanity's fastest spacecraft, the Parker Solar Probe, travels at about 430,000 miles per hour. At that speed, it would take roughly 6,700 years to reach Alpha Centauri. Obviously, that's not practical, but there are proposals on the table for much faster spacecraft. The Breakthrough Starshot initiative, backed by Stephen Hawking before his death and funded by billionaire Yuri Milner, aims to send tiny, light sail-powered probes to Alpha Centauri at 20% the speed of light. At that speed, they could reach the system in just 20 years. These probes, each weighing only a few grams, would be accelerated by powerful Earth-based lasers hitting their reflective sails. During their flyby of the Alpha Centauri system, they'd capture images and data, beaming them back to Earth, a 4-year journey at light speed. If there's a confirmed planet in the habitable zone of Alpha Centauri A, with potential for habitable moons, it becomes the primary target for such a mission. Suddenly, the idea of studying an alien world up close within our lifetime shifts from science fiction to genuine possibility. But let's zoom out for a moment and talk about what this means for the search for life beyond Earth. The discovery of Proxima b in 2016 was exciting, but red dwarfs are problematic hosts for life. They're small, cool, and incredibly active, unleashing devastating stellar flares that could sterilize nearby planets. Any world orbiting in a red dwarf's habitable zone would be tidally locked, with one side permanently facing the star and the other in eternal darkness. The temperature extremes and radiation bombardment make habitability questionable at best. Alpha Centauri A and B, however, are different. They're sun-like stars, stable, well-behaved, and capable of providing steady, life-friendly conditions for billions of years. If we find planets in their habitable zones, especially rocky worlds or potentially habitable moons, the chances of life existing there are significantly higher. And here's the thing. If there's one gas giant around Alpha Centauri A, there are probably more planets we haven't detected yet. Planetary systems tend to have multiple worlds. Our solar system has 8 planets. The TRAPPIST-1 system has 7. It's extremely unlikely that Alpha Centauri A has just one planet and nothing else. There could be rocky, Earth-sized worlds orbiting closer to the star, hidden beneath the glare that even WEBB can't penetrate yet. There could be additional gas giants farther out. There might be an entire solar system around Alpha Centauri A, and we've only just glimpsed the first member. The same goes for Alpha Centauri B. If Alpha Centauri A can host planets in such a chaotic gravitational environment, there's no reason Alpha Centauri B can't have planets too. We just need the right technology and the right observing strategies to find them. This brings us to a broader point about exoplanet science. For decades, we've been finding thousands of planets around distant stars, most of them hundreds or thousands of light years away. These discoveries have been incredible, revolutionizing our understanding of planetary systems and revealing a universe far stranger than we ever imagined. But those distant planets are, in a very real sense, untouchable. We can study them with telescopes, measure their masses and sizes, analyze their atmospheres, but we'll never visit them. They're simply too far away. Alpha Centauri is different. At 4 light years, it's right there, cosmically speaking. It's practically in our driveway. If we confirm planets around Alpha Centauri A and B, they become the most important worlds beyond our solar system. Not because they're necessarily the most interesting or the most likely to harbour life, but because they're reachable. Within this century, we could send probes to Alpha Centauri. Within the next century, we might send crewed missions. It sounds like science fiction, but so did landing on the moon 100 years before it happened. The James Webb Space Telescope's discovery of this planet candidate is just the beginning. It's a glimpse of what's possible when we push our technology to its absolute limits, when we dare to look at the seemingly impossible and say, let's try anyway. Over the next few years, as more observations come in, as Roman launches and adds its capabilities to the search, we'll learn whether this planet is real. If it is, the next question becomes, what else is hiding around Alpha Centauri? Are there rocky planets closer in, baked by their star's heat? Are there icy worlds farther out, similar to our own Kuiper Belt objects? Are there moons orbiting this gas giant, some of them potentially harbouring oceans beneath icy crusts? And the biggest question of all, is there life? It might seem premature to even ask that question when we haven't even confirmed the planet yet, but consider this. Alpha Centauri A is 4.85 billion years old, almost exactly the same age as our Sunday. If planets formed around it early in its history, they've had nearly 5 billion years to evolve. Life on Earth emerged relatively quickly after our planet formed. The oldest evidence of life dates back about 3.7 billion years, less than 1 billion years after Earth coalesced. If a habitable world exists around Alpha Centauri A, and if that world has had liquid water and stable conditions for billions of years, it's not unreasonable to speculate that life might have emerged there too. We're not talking about little green men or advanced civilizations, though who knows. We're talking about the possibility of microbes, of simple organisms, of the basic chemistry of life taking hold on another world. Even that would be the most profound discovery in human history. The philosophical implications alone are staggering. For thousands of years, humanity has wondered, are we alone? The discovery of even the simplest life on another world would answer that question with a resounding no. But we're getting ahead of ourselves. First, we need to confirm this planet. Fall 2026 will be crucial. If Webb's next observations detect the planet candidate again, the astronomical community will be electrified. If the planet doesn't show up, we're back to the drawing board, though even that wouldn't be the end, as there could be perfectly good explanations for another non-detection based on the planet's orbital position. What we do know is this. The James Webb Space Telescope has given us the most tantalizing hint yet that our nearest stellar neighbor, a sun-like star just 4 light-years away, might host a planetary system. That system might include a gas giant in the habitable zone, and that gas giant might have moons where liquid water flows. For the first time in history, we're not just speculating about worlds beyond our solar system. We're directly imaging them, studying them, and preparing to visit them. The age of interstellar exploration, once confined to the realm of science fiction, is beginning to dawn. So, the next time you look up at the southern sky and see Alpha Centauri shining brightly, the third brightest star in the night sky, remember, there might be a world there orbiting in the habitable zone of our sun's closest twin. A world where, just maybe, we might one day find that we're not alone in the universe after all. The cosmos has kept its secrets for billions of years. But now, armed with the most powerful telescope ever built and the determination to push the boundaries of what's possible, we're finally starting to uncover them. Alpha Centauri was always our closest neighbor. Now, it might become our first interstellar destination. And it all started with a faint dot of light, 10,000 times fainter than its host star, captured by the James Webb Space Telescope in the habitable zone of the star next door.